Hello, everyone, once again. We're continuing with paper 2 from Physical Sciences, grade 12, November 2023. Questions 1 through 8 have been done in previous videos, and now we're going to go through the final question on the paper, which is question 9. Again, we're dealing with electrochemistry. It's a short question, only 12 marks, but every mark counts. So without delaying any longer, let's get into the question. An electrolytic cell is set up to purify a piece of copper that contains silver and zinc as impurities. A simplified diagram of the cell is shown below. Electrode R is impure copper. So this is the impure copper. Maybe let's just write that down just to keep track. And they told us that there is silver and zinc as well. So that's important. Okay. So some power source, some other electrode Q, and some shared electrolyte. So this is not a galvanic cell. As we saw in question 8, when you separate your two electrodes and they have different electrolytes, this is a galvanic cell. When it's set up like this is something more of what we would expect an electrolytic cell. This is something you'd find in real world applications. Okay, so the first thing, define the term electrolysis. So this is unfortunately just the definition you have to memorize. Let's define electrolysis as the chemical process in which electrical energy is converted to chemical energy. That's a very simple definition that you can just memorize. There's a couple of other acceptable definitions. You can say the use of electrical energy to produce a chemical change. That's acceptable. You can phrase your answer slightly differently as long as you capture the essence of what the question's asking. You can say decomposition of an ionic compound by means of electrical energy, the process during which an electrical current passes through a solution. Yeah, all are acceptable. But essentially, it's joining electrical energy and chemical change is the bottom line for this question. Okay, moving on to 9.2. Write down the reaction taking place at electrode Q. Okay, so let's think about this for a second. All right. Another clue that we didn't see is this. Okay, so we were told that we have zinc and silver. Zinc and silver as impurities in our copper electrode. And we see silver coming out. So basically, silver is coming out of this electrode. So we need to use that information to try and determine what is happening at Q. And basically, I'd say the best way to purify this electrode is to have copper. So the copper that's in this electrode go into solution, and hopefully our electrolyte may or may not have copper, and it deposits at Q. So we need copper to reduce. And if you remember, oil rig, when it reduces, it gains electrons. That basically means it can go from something like copper 2 plus to copper solid. Okay, if we add 2 electrons. So this is kind of like something that we need to happen. Yeah. So with that in mind, we're just going to make some assumptions here. And we're basically going to say that at electrode Q, where we're collecting our purified copper, which is what makes sense to me of how to set this up, um, we would have probably something like copper 2 plus 2 electrons going to copper solid. It's the best way to purify the copper electrode, to just have copper deposit on Q. There's a couple of other answers that would be acceptable, but this is the only one that will get you full marks. It's the only one that makes sense. You could have the reaction going the other way. That's not incorrect. You will get like a mark for it. But to get the full 2 marks for this question, this is the only acceptable answer. It's the only one that makes sense. It's a bit of a tricky one to figure out, I'm not gonna lie. But if you just stop and think, how would I purify copper in this situation? It only makes sense that simply try and have it deposit on the electrode at Q. Okay. 9.3. In which direction do the electrons flow in the external circuit? Choose from Q to R or R to Q. So, which way are our electrons flowing? This way or this way? Now, we've just said that at electrode Q, we have a reaction whereby um, electrons are being gained. So those electrons have to come from somewhere. So at Q, so here we have copper 2 plus 2 electrons going to copper solid. Yeah. So the key thing here is, where do these electrons come from? Because the copper 2 plus comes from solution, but the electrons have to come from the external circuit. So that's the first clue, that the electrons are probably flowing from R to Q. R to Q. So unfortunately, this is one of those situations that if you get 9.2 wrong, or you write the reaction in the reverse order, you'd also get 9.3 wrong, unfortunately. So you just have to be careful. Moving on to 9.4, calculate the current needed to form 16 grams of copper when the cell operates for 5 hours. All right. They want us to do some math, so let's do some math. It's always a good thing to just write down the information you have. So 16 grams, 5 hours is the same as multiplying by 60 to get it in minutes. 300 minutes multiplied by 60 again is the same as 18,000 seconds. All right. So let's first figure out, let's get our values in moles. So 16 grams of copper. How much is that in moles? So moles is M over MR, which is 16 grams. And the molecular mass of copper is roughly 63.5 grams per mole. And this will give us roughly 0.25 moles. Okay, so that's the first step. Next, we need to figure out the number of atoms of copper. um, so to figure out the number of atoms, we're going to use the simple equation. Number of atoms of copper. Okay, so this equals N over Na, Avogadro's number, which is basically yeah, if we substitute in, this gives us yeah, so I just got a bit mixed up with my notation. So this is basically the moles. N is moles. N is the number of atoms, and Na is Avogadro's number. So substituting in, we should have something like 0.25 here. Avogadro's number is basically 6.02. You can just round it off, times 10 to the 23, right? Rearranging to get n comes out to be 1.5 times 10 to the 23 atoms. And remember that what we really want is the number of electrons, and copper is copper 2 plus. So it takes 2 electrons to get copper solid. Okay, so this is really important, which means to get the electrons, we multiply n times 2, and we get 3 times 10 to the 23. Okay, so now we have the number of electrons. We can carry on. So there's a simple equation that we just have to know, which is there are some equations given at the end of the paper as well, but it's just good to memorize this, and that is the number of electrons, right? Is Q over E, or you can choose your notation. Sometimes this is written as QE, but it's basically the charge of the electron, and we want to figure out Q, right? We want to figure out Q. So thus rearranging for Q, if I can write neatly, rearranging for Q, we have our number of electrons, right? Number of E times the charge, which here it's 3 times 10 to the 23, and our charge is 1.6 times 10 to the negative 19 coulombs. And solving this, we get about 48,160. Okay, coulombs. So this is the total amount of, call it, electricity or electrical charge that we would need to drive this reaction to get 16 grams of copper. So the question, if we just go back to the question, what do they, oh, this has units of C, coulombs. What does the question actually want from us? Calculate the current. Okay, so we know how much charge we need, and we know how much time. So we have charge and time. So from charge and time, we can then figure out current. So using the equation, the current equals charge over time, or maybe let me use a small t to denote time. Therefore, our current equals this over our time of 18,000. And this equals roughly 2.68 amperes. And this is our final answer. Okay. So lots of steps here. I always first like to, let's just write down the information we're given. And then because we're given the mass of copper, let's get it into moles. Once we have the moles, let's get the number of copper atoms. So we get the number of copper atoms, but then we must remember that we need 2 electrons per atom. So multiply the number of atoms by 2 to get the number of electrons. This is the number of electrons. And then we basically want to figure the charge on all these electrons. What's the total charge for this big number of electrons? So we multiply, to get the total charge Q, we multiply the number of electrons by the charge of a single electron, which is what we do here. And we get the total charge required for the reaction. Then now that we have charge and we're given time, we can calculate current, and we get the final current required. Okay, So it's a very long question, but if you just break it down into each step, you'll be able to work through it. Okay, the last question of the paper. During this electrolysis, only copper and zinc are oxidized. Give a reason why the silver is not oxidized. So again, for this one, as very similarly that we did in question 8, we're just going to go down to our reaction potential tables, and we realized that the way we're driving the reaction, silver has a much higher reduction potential than copper and zinc. So, okay, let's ignore copper 1 and just focus on copper 2 plus. And we can see that it has a higher reduction potential. So, yeah, look, zinc is way down here. So there's zinc, it's copper 2, silver 1. So, unfortunately, the way the reaction is set up, because silver has a higher reduction potential than copper and zinc, silver won't be oxidized in the reaction. Only copper and zinc will. For this reaction, it's fine because we only care about purifying our copper, but this is the reason why. So if silver was, let's say, below, somewhere below here or below here, then the reaction would work. But because it's higher than copper, it doesn't work. So that's basically the reason for this. So how do we phrase that? So you could say silver is a weaker reducing agent than copper and will not be oxidized. That's one way of phrasing it. You could also say the voltage of the power source is not effective enough to oxidize silver. And the reason for those two answers, the reason behind them is simply because silver has a higher reduction potential than copper. And that concludes question 9. And with that, that concludes this entire question paper.